For thousands of years, iron was the most useless metal on Earth. It was everywhere. About 5% of the planet's crust is made of it. Ancient farmers walked on it. Their children kicked it around in the dirt. But nobody could do anything with it, because iron had a problem that no ancient civilization could solve. Bronze melts at roughly 950 degrees Celsius. The best furnaces of the ancient world could reach about 1,150. Pure iron refuses to melt until 1,538 degrees. That gap, almost 400 degrees beyond anything humans could produce, made iron ore look like nothing more than heavy red rock. There is archaeological evidence that ancient metalworkers actually tried. They threw chunks of iron ore into their copper smelting furnaces, cranked the heat as high as it could go, and waited for liquid metal to pool at the bottom. Nothing happened. The rock sat there, glowing and useless. So the people who built the pyramids, who engineered massive trade networks across the Mediterranean, who cast beautiful bronze weapons and tools, looked at the most abundant metal on the planet and concluded it was garbage. They were wrong, but it would take a freak accident to prove it. Before that accident, the only iron humans could actually work with came from space. Meteorites, fragments of ancient asteroid cores, occasionally survived the plunge through the atmosphere and landed on the surface carrying pure metallic iron mixed with nickel. Ancient people recognized immediately that this material was different from anything in the ground. It was dense, workable, and rare enough to be treated as sacred. Long before the Iron Age officially began, Egyptian craftsmen were hammering meteoritic iron into ceremonial objects. A study published in 2016 confirmed through X-ray fluorescence analysis that the iron dagger found in Tutankhamun's tomb, dating to the 14th century BCE, was made from a meteorite. The blade contained roughly 10.8% nickel, a composition that closely matches iron meteorites and rules out terrestrial smelting. During the Bronze Age, this celestial metal was valued more highly than gold, but you cannot build a civilization on falling stars. The supply was too unpredictable, the quantities too small. To unlock the iron buried in the ground, humanity needed something it did not yet have, and the path to finding it had nothing to do with iron at all. The real bottleneck was not temperature alone, it was chemistry. Iron ore is mostly iron oxide. The iron atoms are locked in a tight chemical bond with oxygen, and breaking that bond requires more than just heat. It requires a specific chemical reaction that strips the oxygen away. Ancient metalworkers did not understand any of this. They were not trying to invent iron technology. They were trying to make their existing copper furnaces work better. The upgrades came gradually, over generations, each one solving a practical problem. First, smelters switched from burning raw wood to charcoal, which produces significantly higher and more consistent temperatures. Then they started building taller clay chimneys around their furnaces, discovering that an enclosed vertical shaft creates a natural draft, pulling fresh air upward through the burning fuel. Finally, they added leather bellows, pumping forced air directly into the base of the fire. Each improvement was designed to produce better copper. None of them were intended to do what they actually did. Inside these hotter, more enclosed furnaces, something unexpected was happening. The burning charcoal, starved of outside oxygen, was producing large amounts of carbon monoxide gas. As that gas rose through the chimney, it passed over the chunks of iron ore sitting in the fuel bed. Carbon monoxide is violently attracted to oxygen. When it met the iron oxide, it ripped the oxygen atoms away from the iron and carried them off as carbon dioxide. The rock did not melt. It could not melt at those temperatures. Instead, the iron inside it was chemically released while the rock remained solid. The oxygen left, and what stayed behind was metallic iron, still trapped in a porous, spongy mass, offit, and waste material. When an ancient smelter broke open the bottom of the furnace, expecting a clean puddle of copper, they found something strange. A lumpy, ugly, glowing mass that did not look like any metal they had seen before. It was called a bloom. It did not shine. It looked like a mistake. But when someone hit it with a hammer while it was still white hot, it did not shatter. It bent. That moment was the beginning of the Iron Age. But the metal that came out of the furnace was not yet useful. The bloom was structurally a mess, full of slag and impurities and air pockets. Turning it into something functional required a second breakthrough, and it was just as accidental as the first. Blacksmiths discovered that beating the bloom repeatedly while it was hot did two things. It squeezed out the glassy waste trapped inside, and it forced the scattered iron particles to bond together at an atomic level. The result was wrought iron, a metal that was tough, flexible, and could absorb impact without snapping. There was a catch. Wrought iron was softer than high-quality bronze. A wrought iron blade would dull quickly and deform under heavy use. If iron had stayed in this form, it might never have replaced bronze at all. But blacksmiths noticed something they could not explain. When iron sat in a glowing charcoal hearth for a long time, it changed. It became harder. What was happening, though no one would understand the chemistry for thousands of years, was that carbon atoms from the charcoal were migrating into the iron's crystal structure. At high temperatures, the internal lattice of the iron opens just enough to allow carbon atoms to slip between the iron atoms and lock into place. They were making steel without knowing what steel was. When a blacksmith took this carbon-infused iron and plunged it rapidly into cold water, a process later called quenching, the crystal structure froze into a state hard enough to scratch bronze. The metal could hold a sharp edge, absorb shock, and outlast anything else available. A blacksmith with a charcoal fire, a hammer, and a bucket of water could take a dull red rock from the ground and turn it into the hardest blade in the ancient world. It is easy to understand why nearly every ancient mythology includes a god of the forge. Even with this capability, iron remained a secondary metal for centuries. Bronze was too established. The kings relied on it, armies were equipped with it, and enormous trade networks existed to supply the copper and tin it required. Those networks were also its greatest vulnerability. Bronze requires two metals. Copper is relatively common, but tin deposits are rare and geographically concentrated. Ancient empires maintained supply chains stretching thousands of miles to secure their tin. If a single merchant fleet sank or a conflict disrupted a key trade route, an entire civilization could lose the ability to manufacture its most important material. Around 1200 BCE, that fragile system broke. A convergence of climate shifts, widespread drought, mass migration, and warfare destroyed the major civilizations of the Eastern Mediterranean within a few decades. The Hittite Empire collapsed entirely. Mycenaean Greece fell into a dark age that lasted centuries. Egypt survived, but barely. The elaborate international trade networks that had supplied tin for generations disintegrated. Without tin, there was no bronze. Without bronze, there were no weapons, no tools, no infrastructure. And suddenly, the furnaces that had been quietly producing spongy iron blooms as a niche side project became the most important technology on the planet. Iron ore was everywhere. A village with a clay furnace and access to a forest for charcoal could produce its own metal without relying on any trade route at all. For the first time in human history, metal tools were not restricted to kings and elite warriors. A farmer could own an iron plow. That plow changed the world more than any sword. Iron plows could cut through heavy, clay-rich soil that wooden plows could not scratch. Land that had been considered useless for agriculture was suddenly productive. Food supplies increased dramatically, and populations grew to match. This was not limited to the Mediterranean. Across the globe, different civilizations were solving the same chemical problem through entirely independent paths. In China, engineers pushed furnace temperatures high enough to actually liquefy iron, developing cast iron technology centuries before Europe reached the same point. In India, metalworkers sealed iron and carbon together in clay crucibles, creating a material called Wootz steel, known for its extreme hardness and distinctive surface patterns. European crusaders would later encounter this metal and call it Damascus steel. In sub-Saharan Africa, engineers designed tall, natural draft furnaces that preheated the incoming air, achieving remarkable thermal efficiency without mechanical bellows. Each of these traditions arrived at the same underlying chemistry through different engineering. When the Industrial Revolution reached full speed in the 19th century, innovators like Henry Bessemer figured out how to blast air through molten iron, burning off impurities with enough precision to mass-produce structural steel. That steel made skyscrapers, railways, bridges, and cargo ships possible. But the core reaction inside a modern billion-dollar blast furnace is fundamentally the same one that happened inside a mud brick chimney 3,000 years ago. Carbon monoxide stripping oxygen from rock. The scale changed, the engineering changed, the chemistry never did. The person who pulled that first ugly, spongy bloom out of a broken furnace had no idea what they were holding. They were not trying to launch a new era of human civilization. They were probably just confused about why their copper smelt went wrong. Every steel beam in every building you have ever entered exists because of that confusion.